Sound begins as physical energy. Before a microphone ever captures it, it exists as a displacement of molecules in the air, vibrating against solid surfaces in a chaotic, three-dimensional environment. To process that energy, we must digitize it. We collapse that physical wave into a one-dimensional time series signal, essentially a long list of numbers representing amplitude over time. Capturing biological and physical processes as 1D timelines is a foundation of modern diagnostics. We see this in the continuous peaks and valleys of an EKG, which monitors the electrical rhythm of a heart along a single axis. But a 1D audio waveform hides as much as it reveals. To identify the specific pitches and tones within that line, we use the fast Fourier transform, or FFT, to extract the individual frequencies. This chart shows the resulting power spectral density. The FFT identifies the exact frequency spikes present in the signal, showing us the strength of each pitch. However, this operation comes with a specific cost: the destruction of temporal context. While the FFT provides mathematical certainty about what frequencies exist in a file, the calculation itself erases the record of when those frequencies occurred. This missing time variable is an immediate roadblock for audio AI. Audio machine learning models rely on chronology to distinguish between syllables in speech or notes in a melody. To prepare audio for a model, we must move beyond the 1D sequence and translate the data into a 2D time-frequency representation. The algorithm used to recover this lost time dimension is the Short-Time Fourier Transform, or STFT. The STFT isolates a small segment of the raw signal using a sliding window function. It analyzes data within that window before moving forward. An FFT is computed for each discrete frame, generating a heat map mapping time and frequency onto a 2D plane. We call this matrix a spectrogram, the foundational feature used in audio machine learning pipelines. But the spectrogram is governed by a rigid constraint, the time-frequency uncertainty trade-off. To see this trade-off, we test a signal changing every 2 seconds. A short 128 sample window gives excellent time resolution with exact transitions, but blurred frequencies. A large 512 sample window yields precise frequencies, but time boundaries bleed messily across the marks. Because STFT uses a fixed window size, engineers must choose between timing accuracy or frequency accuracy. You cannot maximize both at once. This rigid linear resolution is inefficient for speech AI. It treats every frequency band with equal mathematical weight, regardless of importance to the listener. The solution lies in biology. Human auditory perception is nonlinear. We do not hear all frequencies with equal clarity. At the low end of the spectrum, our ears are highly sensitive. We can easily distinguish between a 100 Hz and a 200 Hz tone, but at the high end, that sensitivity disappears. Most people cannot distinguish between a 5000 Hz tone and a 5100 Hz tone, even though the absolute difference is the same. Feeding a linear STFT into a neural network wastes GPU power calculating high-frequency details that have no perceptual value. The Mel scale was engineered to resolve this by remapping frequencies to match human hearing. A linear axis morphs into the Mel scale, expanding low frequencies and compressing highs. We build a filter bank of overlapping triangular windows. They pack densely at the low end to preserve speech resolution and widen at the high end to compress perceptually ignored data. By utilizing the Mel filter bank, we shift computing resources to focus on the frequency ranges where human hearing is most discriminative. The Mel scale isn't just about acoustics. It is an act of mathematical dimensionality reduction. This column represents a single window frame of STFT data with 513 frequency bins. We square their magnitude, turning amplitude into power, then calculate the dot product against our Mel filters. This compresses the data into a smaller vector called Mel band energies. Reducing the data from 513 bins down to 128 discards acoustic noise while keeping the information most relevant to human listeners. This process is repeated for every time frame in the audio file, sliding the window from beginning to end. When these vectors are stacked, they form the final Mel spectrogram. Next to the original STFT matrix, the scale of reduction is clear. This 128 by 230 tensor is the actual payload. It is the specific feature matrix used in libraries like Labrosa to train audio models. By solving the time problem with the STFT and the dimensionality problem with Mel scaling, engineers have created a machine-readable architecture tailored specifically for human sound.